Yes, am I audible? Hello.
Yes, sir.
Yes, am I audible? Hello.
Yes, audible, sir.
Okay. So we'll start within 2 to 3 minutes. Okay. Let the people join.
Okay.
So we'll start. Hello. Hello. Am I audible? Yes. Hello. So I hope am I audible? Hello. If you guys have some doubt, you can start asking. Meanwhile, others can join. Okay. So any doubts you faced while solving the problems, you can just ask and I can clarify before starting the session. Any doubts while solving these StatCom problems of the assignments or previous assignments, you can ask.
Sir, a doubt is there.
Yes, so please ask the doubt.
Sir, while calculating the KV rating of the compensator,
Yes.
Whether it depends on the three-phase load or single-phase load?
See, it depends whether the system is actually what system you are dealing with. If you are dealing with single phase systems, obviously it depends upon what the load reactive power is there, and accordingly you use the DStatCom to compensate for the load reactive power demand. So it depends on multiple things, not only the nature of load or the nature of the system, but also on the type of functionality you are trying to deploy by using the DStatCom. For example, you are deploying the DStatCom only to compensate for the load reactive power demand. Then obviously your KVA rating of the DStatCom will depend upon the KVA rating of the rating of the load, I can say, and the power factor of the load. So from that you can calculate the reactive power, and accordingly that will be the rating of the DStatCom. But for example, your DStatCom is also used to process some active power by connecting some solar arrays or some other kind of processing units that you have connected. So the DStatCom rating will also depend upon, that is the rating, what is the meaning of rating of a device. The meaning of rating of a device is how much power it needs to process. Now, if the DStatCom is only connected to supply for the load reactive power demand, then your DStatCom KVA rating is only the reactive power, that is what is the reactive power of the load by power balance. But if it has to process some additional power, active power, then you do some kind of this, that some Q that he has to process the DStatCom to compensate for the load reactive power demand, for example QL. And along with that, it also needs to process, for example, some P. Then total KVA rating becomes Q square plus P square whole root over. This is S net. So like where you can calculate the KVA ratings. You need to see what kind of system it is and what are the functionality that you are trying to achieve by using the DStatCom. After reading the full question, you can understand that what the DStatCom is used for. Accordingly, you calculate. Likewise, we also solved the previous session. We solved the problem also. We calculated the DStatCom current rating, and then we calculated the KVA rating also. But how we were calculating the current rating? By studying the system, and then by the information of the load side and the supply side, we just calculated the DStatCom current, and then accordingly we can also calculate the KVA rating. So likewise, actually, the system you need to see first. So hope it is clear. Any more insights you need while solving the problem, or some steps you are facing difficulty, you can just ask.
Yes, sir.
But any more doubts? Any problems while solving you faced the difficulties? Or it appeared that it hasn't been covered, those concepts? You can just highlight and we can discuss. Before starting, because we are moving into the new topic. So for that, I need to ensure that you don't have any doubts while solving the compensator problems or the DStatCom, all those problems. So then just any one of you can just highlight and we can cover those before going into the new problems. So please see and let me know if you have more doubts. I give you some time for 2 to 3 minutes and just can see, and I will cover up those concepts. Yes. So any more doubts? So let me see who all are in the meeting and can just ask one by one. Yes. So Ranveer Patil, do you have any doubts?
No, sir.
Okay. Okay. And there is, I think, Umakant Yerge. Do you have any doubts? Any of you can just ask before going on to the new problem sets. We can just clarify the doubts.
No, sir.
Okay, so up to this it's clear, I think, maybe. So hopefully I have also covered most of the concepts. And if you have meanwhile some doubts, you can also write in the group and we'll address the doubts there only. So I assume no one has any doubt till this point, and so we'll move on to the next set, right? So starting from the previous session where we ended, we were solving some problems on static series synchronous compensators, series compensation techniques. So there we left the session with this problem where we had this load impedance as 7 plus J7. It was a lagging load, and the information is given that it is a single phase load and the supply voltage is 230 volt 50 hertz, and your aim is to realize it, that is this load, to the supply as a unity power factor load, that is virtually make it appear to the supply that it is a unity power factor load attached to the AC system. And also you have to maintain another point is given. So one point very important, it is to be realized as unity power factor load. Please read the problem and then start solving, because there are few points which are important. And another is you have to maintain the rated load voltage. That is rated means the given 30 volts. So you have to achieve both the targets using this static series synchronous compensator. So you know that it looks, this is a device which looks like this, or I can draw like this. And since it is single phase, how many switches will be there in the inverter? Anyone? So kind of this. Okay, this is a device, and here is the
So
load
there is
connect.
inductance. So there is also inductance in series with this.
Which inductor?
LR here.
Yes, yes. Just the notation I am drawing. All the interfacing inductances are there, and you have to connect this along with in series with that. All those are there, but just to symbolize it, it is used. So all inductances are here. So everything is there, and you have the load also. Right. Point is that what you are trying to do, you are trying to achieve this load voltage as per the rated voltage, and your supply current should be in phase with the supply voltage, right? So this is ZL. So previous week what we did, we assumed the load to be 7 plus J7. Now my question is, if the load is 7 minus J7, what will happen? And assume for the timing, assume no source impedance. Okay. So no source impedance is there. In that case, I want you to see if there is really any change by making changes in the nature of the load. Last week we ended the session by targeting lagging loads, and we determined all the three. And now my question is, if I replace it, for example, with some leading loads, assuming no source impedance, then what will be the whether at all there will be any change in the current rating or voltage rating or VA rating. So just think about it and tell me how to solve. Let's start solving the problem. Gradually we'll get the clarity. So now the problem is leading loads. Okay. So I have connected this type of load 7 minus J7. The impedance of the load is given as this. Consider 7 minus J7. And now you have to achieve all these two targets. So how will the phasor diagram look like? So after, I can say after compensation, assuming that you have controlled the system and achieved both the functionalities, then how will your phasor diagram look like? So if I draw like this, assume this is the VS, which is 230 angle 0. Then what will be the nature of IS? Anyone? Just read the two targets that you had to achieve, and now assume you have achieved those targets using control, proper control. Now how will IS look like if VS is like this? Yes.
Leading power factor.
No. You have achieved unity power factor, na? Your target is that. So after compensation, you must have achieved unity power factor.
So it
Your
is in phase with supply voltage.
yes, it is in phase with supply voltage. And since this is a series connected network, so how will my IL look like? Same as IS. Now, also you have achieved load voltage. Load voltage that is equal magnitude with that of your supply. So how will your VL look like? Can anyone tell me? What is VL actually? It is IL into ZL. IL I know how IL looks like. So IL into ZL will be how? IL is having angle 0. In the phasor diagram you can see. Now if I multiply IL with something which is ZL, and ZL is looking like how? 7 minus J7. So you can say 7 root 2 angle minus 45 degree. Everyone is clear with this step? How I am doing this? Just let me know if you are not comfortable with the polar transformation. So if you are clear, because I always and I remember in the some sessions before. So if I assume that ZL is like this, okay, so it is leading power factor load. So how will IL into ZL look like? When you are multiplying two phasors, the angle gets added. So in your IS or IL, both are same, into ZL will be VL. So VL will be something like this. Sorry. Yes. This 45 degree or minus 45 degree I can write. Here because IL into ZL. L is IL into ZL. Now don't assume it to be a cross product, okay? I'm just multiplying the two phasors. So, but also one information we have that both are equal in magnitude. So your PL will be having angle 40 minus 45, but your amplitude of the VL will be same as that of VS. So current rating you can easily calculate. What is current rating of the compensator? You can just do after compensation VL by ZL, and VL by ZL means 230 by 7 root 2. Just find out what it is coming. This is the current, which is the load current, and that load current is flowing through the compensator also. All are in series, all are same. So that is the current rating of the compensator. So even if you have some leading loads or have some lagging loads, this 7 root 2 amplitude will come same. And you see that there, for the time being, you see that there is no difference in lagging or leading loads. Your current rating is coming the same. Okay. Now just hold on. Okay, just tell me the current rating. What is the current rating coming? Yes. What it is coming? Just do with me such that it is helpful to you. Okay.
23.23.
So same answer we got. previous week also. So for the time being, you see difference is coming. So let's calculate voltage rating also. So what is voltage rating? You know, the thing Vs plus V some compensator equal to VL. So V compensator is VL minus Vs. As for KVL, this is Vs, this is V compensator, and this is VL. So V compensator is VL minus Vs, which is 230 angle minus 45, which is the load voltage minus 230 angle 0. Calculate what it is coming. VC. What is V compensator coming? Just calculate this. What is VC coming? Just you can tell me mode of VC. No need of the angle. Because we are trying to determine the voltage rating. When we are working with ratings, then phase does not matter. You can just give me answer in amplitude only, and obviously phase matters for calculating the amplitude, but after calculating you don't need to calculate the phase also, just can calculate the amplitude. So what is 230 angle minus 45 minus 230 angle 0 coming? So any of you solved, or I will write the answer? So you see, if you analyze, then you are getting same voltage rating of the compensator as it came in the previous problem which we did for the lagging loads. So till now you see that if load amplitude, that is load impedance, is same, whether it is lagging or leading, if you assume no source impedance, then your compensator rating will be same. Okay, this part I think is clear. So V compensator, this amplitude is coming 176 volts. And obviously, if you have both the current rating and the voltage rating, which is this, and current rating I think is this. This is I compensator amplitude. So your KVA rating, someone was asking, how will I calculate KVA rating? It is nothing but voltage into current. Since it is single phase, if it was three phase, then you have to multiply with 3 also, because per phase we do and then multiply with 3. So obviously for a single phase, it is only voltage times current. So what is coming? It 176 into 23 point. So it is coming around 4.088 kVA, right? So till now you see that assuming no source impedance, your kVA rating of the compensator does not change. Now let's move on to the next problem. Okay, just keep it in mind. Okay, we'll come back to this discussion after solving this problem. So now you have this source impedance. Okay, where you have been given that the single phase supply has some source impedance. And just can you tell me, from because you have also seen the lectures, you must have been clear with this concept. So
Sir,
where we
I have doubt.
yes, yes,
Sir, VA rating we have calculated, and if it is a suppose three phase, we have to multiply it by 3.
yes, just please repeat your problem. You just
Sir, you said that if it is a three phase system, then we have to multiply it by 3.
correct,
VA
correct.
rating, and suppose
Yes, yes. Please
so
go ahead.
sometimes we also multiply by root 3, sir.
Correct, because I will clarify this concept. I think this is creating some kind of confusion. So you see, while calculating three-phase power, na, yes, while calculating three-phase power, or I can say apparent power also. Okay, what you do root 3 times V line to line times I line to line. Okay,
Yes,
assuming
yes,
a balanced system. Now also you can do 3 times V phase to phase into I phase to phase.
yes, yes.
Assuming balanced system. If your system is not balanced, you can do V phase to phase 1 into I phase to phase 1 plus V phase to phase 2 times I phase to phase 2 plus V phase to phase 3 into I phase 2 phase 3 for an unbalanced system. You take the per phase powers and add them up. And obviously, if you want to calculate some active power or reactive power, just multiply it with cos phi or sin phi, right? Accordingly. So I think this is the approach, because you can do line to line also, but and also face to face. But be careful that it has to be a balanced system. If it is not balanced, then we must have solved some kind of this problem that face to face we need to do individually. Those thyristor based problems, right? Where you have different kind of loading on three different phases. Then obviously before load balancing, if someone asks you to calculate, obviously the load end calculation is more appropriate, because power balance will hold, right? Whatever is the active power demand of the load, that will be supplied only. No additional power will be there. So load end you can also calculate what is the node voltage across the load, and then the current going into the load, and accordingly you determine the power. So that is also one approach. So accordingly, because we are trying to find out the volt ampere rating for a single application, we just take the voltage and current and multiply them. For a three phase, obviously it will be 3 times per phase I am talking. Line to line, then root 3 into line to line voltage into line to line. But obviously phase to phase analysis we are doing. We are drawing the phasor diagrams for per phase basis. That's it. We do 3 times for a 3 phase system. Hope this is clear, okay? Till now we did not assume effect of source impedance, which is a very important parameter for these kind of problems. Now we brought the source impedance into picture, and I will tell you beforehand that it will bring drastic changes into the calculation if you consider the source impedance, because then the nature of load will dictate how the kVA rating will be coming. That is, you will get more kVA rating, whether you need to install more kVA rating compensators or lower kVA rating compensators will be declared to some extent by the source impedance. Because source impedance naturally will be inductive in nature, but that will govern the choice of the compensator ratings depending on the load, how the load is, lagging load or leading load. Till now, we did not have any problem. Till now, the source impedance was not there, and hence the choice of compensator ratings based on only whether the load was lagging or leading in nature did not have any significance. Same as you saw two problems we did. But now I brought in the picture of source impedance. So just you will wait and see what happens. Okay. So now read the problem and tell me how it is different from the previous problem. Okay. Just everyone read it, and some of you just highlight what is the main difference you see, apart from the fact that we have included the source impedance into picture. Apart from that, what is the, because here also you need to calculate the volt ampere. So what is the difference? Why I took this problem? There must be some difference, right? So what difference you just can spot apart from the fact that I have included source impedance? What is another difference which is there? Anyone can highlight. Okay, just go through the problem once and then tell me. Yes, you can just let me know. Okay. So you see a word minimum here. Okay. Note this word, because in the previous problem you did not have such minimum terms. Okay. As you can see in the previous problem. So in this previous problem and this problem, what is the difference? Why the word minimum kVA rating came into picture? So any comments on this? Any of you can just highlight your views regarding that.
That means it is a minimum rating we should use to compensate the system.
So why we did not consider it in the previous problem? Why was no concept of minimum coming in the previous problem, and why suddenly in this problem only we are bothered about minimum volt ampere rating? Anyone can just highlight. What is
in
the
previous
point?
problem?
Yes.
There was no source impedance, sir.
No, source impedance is there. Okay, what else? Source impedance does not dictate the minimum, that is minimum volt ampere rating, and source impedance does not have any relation. It has some relation with other things, but minimum volt ampere rating, when we are telling, what is the constraint that we are imposing? One thing I will make you note, in the previous problem, there was a term unity power factor. Okay. Your aim was to maintain unity power factor load at the load side. Okay. So this in this problem, you don't have any such unity power factor there. So what is the meaning is that if you are aiming to deploy your compensator to achieve unity power factor loading, then you inherently are imposing a constraint on the nature of compensator, that is how the voltage should be injected. Because just see this phasor diagram. Okay, just see what I am drawing, you will gain clarity. Okay, so your source voltage was like this. I can write, because taking the source or the supply voltage as the reference, I am drawing. So this is angle 0. You can assume this to be the reference. So what we were doing, first problem we told that we have to maintain unity power factor loading. That is, virtually we need to make it appear to the AC system that it is just like a unity power factor load connected by injecting appropriate voltages. So now what I am doing, if I am telling that I have to maintain unity power factor, I am imposing a constraint on the rating of compensator. Please note these points. Okay. You don't want to maintain unity power factor, you are not imposing constraint on the rating of the compensator. How I am drawing. Okay. So you are constraining to maintain unity power factor means your supply and your supply current and supply voltage should be in line. I think screen is lagging. Second. Are you able to see the current waveform? I think no, right? I will just stop sharing and reshare. Okay. Yes, I hope now it is clear. So previous problem, we were constraining ourselves by using this additional constraint that we have to maintain unity power factor. So this IS have been in line with VS. And what it was doing is IS was equal to IL equal to I compensator, because it was series connection. What it did, IL into, I told you ZL, that should have been VL. So VL was accordingly maybe lagging or leading coming on this circle. Whatever is the nature of the load. If your load was leading nature, then voltage would have been like this. Because obviously it is negative, minus J term is there na, for leading loads. So you multiply your I with that load impedance and your load voltage will be lagging. And if you are having lead that is lagging loads, for lagging loads, you have plus J, that is impedance. So plus J, obviously it will go above. So voltage will be leading, load voltage. So you are constraining your load voltage by deploying this additional fact that you have to maintain unity power factor. So inherently your compensator will have to inject this kind of voltage, V compensator. Agreed or not? You have no other choice. You want to maintain this kind of voltages at the load end, as well as attain power factor like this, that is in line with your supply voltage. You have no choice but to inject this kind of voltages, which are quite large in or I can say quite big in their magnitudes. So when you are talking about your power factor, you are aiming to achieve a particular nature of power factor at the supply side. You don't have any control over minimum volt ampere rating. You can't control the voltage that have to be injected according to attain that power factor. I hope it is clear. Because if you want to attain unity power factor, your voltage will not be in your hand, because that will be dictated by the nature of the load. And accordingly, your compensator should inject that kind of voltage such that load voltage amplitude is also same as supply amplitude. And as according along with that, you need to maintain also the power factor. So you lost control over your compensator voltage. Now, on the other way, I can say if I don't impose any constraint on the supply power factor, then I can control this VC. Now you see, this was without effect of source impedance. Now, if I consider source impedance also, how it look like? Now you see, this is a lagging load, and this is also an inductive reactance. So load current will be lagging in nature, right? So again, you draw PS. This is your supply voltage, and load current would have been lagging in nature, your IL. So what is the, because you have after your source impedance, you have some supply, you have some source impedance ZS, is VS, and here after this you connect the compensator. Hope this is clear, right? So you have your compensator also. This is the device, and after that you connect the load. So the current was lagging the voltage, and Vs minus, what is Zs? Zs is Rs plus Jxs. And what is Zl? RL plus Jxl. So Vs minus IL into Rs, which is like this, and minus JRS into Xs. JRS into Xs, okay? This is JRS into Xs, 90, and this is IS into Xs, and this is IS into Rs, which is the drop of the source impedance, right? So now your voltage is coming, amplitude, that is load voltage amplitude is coming lesser than the source amplitude at this point, because you have the source impedance sitting in between, and it is lagging in nature. It is resulting in voltage drop at this point. But what you want your load voltage to be same in amplitude as the supply. So you need to boost voltage. Okay. So this voltage you want to increase in amplitude, and you want to increase up till this voltage. This is Vs. So I will draw it maybe little bigger so that it is not confusing. I will just remove this diagram. We'll draw bigger, okay, so that it is important concept. So this is your source voltage, and current was lagging in nature, IL. So Vs minus IL, IL or IS all are same because it is series connection, okay. So Vs minus IL into Rs minus IL into Xs, obviously J is there, and this was your voltage at this node. I can say voltage at 1, node 1, V1. So how was your V1? V1 was like this. But you want your VL be equal in amplitude to that of PS. So draw a circle. Now tell me, for any kind of load, what is IL? It is VL by ZL. PL is always fixed. Mod of IL is mod of VL by mod of ZL. ZL is fixed for a particular load, and VL is also what you want to achieve. It is fixed. So IL will never change. But what kind of voltage I need to inject, that is in your hand. Depend or what you want to achieve. So now you tell me, this is your voltage, which is at node 1. In order to make it equal to VL, that is its amplitude equal to Vs, what is the minimum voltage you can inject? because your current is fixed. If you can reduce VL or V compensator, I can say, because what is the compensator rating? V comp equal to I comp into or S comp. The compensator rating is I comp into V comp or VC, you can write. So I compensator is in series with IL or IS, all are same, and it's fixed for a particular load. But V comp is in your hand. Since you have nowhere mentioned in the problem that you have any constraint on the power factor of the supply side. So since you don't have any constraint on the power factor of the supply side, you will obviously choose the minimum rating of the compensator. And how you will do so? Can you tell me from this phasor diagram what minimum voltage you can inject such that it is equal to Vs amplitude, this line? What voltage you need to inject such that your amplitude, voltage amplitude of the compensator becomes minimum? So it should be in phase with V1. You can inject voltages like this also. You can inject voltage like this. You can inject voltage like this. You can also inject voltage in this direction, or in this direction, or in this direction. Voltage injection is in your hand. But if you inject this voltage in phase with V1, then your voltage rating of the compensator becomes minimum. That's why the term minimum VA rating has come. But note, if you select a particular voltage you want to inject through this compensator, you lose your control over the power factor of the supply side. And if you try to control the power factor of the supply side, you lose your control over the injected voltage, how your voltage should be injected. That is, indirectly you lose your control over the minimum VA rating. You will not attain minimum volt ampere rating in that case if you try to control the power factor of the supply side. So load impedance plays a major role in this condition, because obviously the power factors will differ, right? Here and here, these angles also differ. You can see there is little amount of shift in the voltages at supply side and at this node, because in between there is sitting the source impedance. So due to this source impedance, obviously due to this source impedance, you will have different ratings of compensators also that you will see in the next problem. But what I'm telling, for a given amount of source impedance, if you try to control the power factor of the load, or the power factor that is from the supply side for a particular load, then you lose your control over the injected voltage to maintain equal amount of voltage at the load end. And if you, in this problem, as in this problem, you want to attain equal amount of voltage at the load end, you lose your control over the power factor of the supply side. So your power factor of the supply, what it is, the angle between Vs and Is. Just see the angle between Vs and Is. You can mark this as beta, as I am using the same nomenclature as in the lecture. And what is the power factor of the load? I can tell this is the power factor because this is VL, so this is theta. So what I mean, by injecting your minimum voltage, you lose your control over this beta. You cannot attain unity power factor even if you wish to, because you are trying to maintain minimum voltage injection, minimum amplitude of voltage injection by the compensator to minimize the cost of the compensator, the size of the compensator, whatever you can tell, the minimize the VA rating. Because our primary aim is to minimize volt ampere rating, okay, not to maintain the power factor. In this case, if someone asks you, is it possible to maintain unity power factor using minimum VA rating, which we saw in this phasor diagram, your answer will be no. To maintain a particular power factor at the supply side, a particular amount of voltage needs to be injected, and that particular voltage will not be the minimum voltage. This voltage injection will not ensure unity power factor or any kind of power factor. It will have its own power factor, which you see by angle beta. Okay, so this was the point I wanted to highlight. Obviously, the effect of source impedance you will also see will also change, I can say. Like for example, in the previous problem also saw that you are having no difference. Whatever kind of load you connected, the VA rating of the compensator remained the same. assuming unity power factor you have to maintain. But if you consider the effect of source impedance and then you try to do the same problem for lagging and leading loads, you will get different power ratings of the compensator. So just see that problem and let's first solve this and then we'll go to the next problem. So, but current wise it is same. Current calculation is the easiest. Okay. Someone asks you to calculate the current, it is a one line problem. So current wise, can you say the answer in one line? If someone asks you to calculate the current of the compensator, how will you calculate? You know one information is not going to change in all cases, which is the voltage. The load voltage you know is same as that, the amplitude is same as that of the supply. So what is VL? VL is 220 and ZL is not going to change for a given load. It is 20 root 2. What ZL is 20 root 2. Okay. It is not going to change. So what it is coming? This is the load current and same as the compensator current and same as the supply current. This relation will always hold because the topology of the network. Obviously the supply is there. After that the compensator is there. In between the source impedance is there, as you can see in this diagram. After that your load is there. So all are in series and this topology is not going to change. So for this reason only, due to the fact you know that in all cases your series compensator will ensure the equal amount of voltage amplitude at the load point. For that reason, the current calculation is the easiest in these kind of problems. It is not affected by minimum kVA or your normal power factor load. This is always going to hold. So current calculation is easiest. That's why, but you need to understand the difference between the problems. That's why I drew the phasor diagram. So remember one thing, for your volt ampere rating to be minimum, you need to inject in phase voltages to that of the supply, such that your voltage rating is minimum. But in that case, you lose your control. So lost control over power factor. Just remember this point. We lost the control, right? We cannot maintain any power factor, ensuring minimum VA rating, right? What is the current? Just calculate. Let me know the current. What is the current coming?
7.77.
Okay. So 7.78 amperes, right? So problems are very easy, but you need to see beyond the problems because you need to be able to draw the phasor diagram and take a feel. Because then only you can understand why the methodology changes from problem to problem. Because their implications also change from problem to problem, right? That's why I hope you must have understood why the term minimum is given here, right? Anyone having doubt over this term minimum? I can still clarify. Nowhere you can see in this kind of problems it is written about the power factor. Must understand that by ensuring minimum volt ampere rating, you cannot attain unity power factor at the supply side. Hope this is clear, right? From this phasor diagram also it is clear, right? The supply power factor is not unity because then you would have an angle beta equal to 0. But here beta is not 0, as you can also see from the phasor diagram. So unity power factor we cannot achieve, or any other power factor also. A particular power factor only will come for a minimum VA rating. But obviously our voltage injection amplitude is minimum, and cost of compensator also comes down. So it has its own application in different other areas which we want to focus on, and it obviously changes your application also from application to application. Maybe in distribution systems, all you need unity power factor obviously to minimize the line losses. But sometimes in bigger systems where there are very nearby systems and you need to minimize you have very large compensators, you need to minimize their ratings as much as possible, such that the cost comes down and cost efficient. So performance versus your application, so those comes different, right? You can do the trade-off between cost and performance. So that is the whole game, right? But these problems give you different aspects based on some different applications, right?
Yeah, sir, I have a doubt, sir.
Yes.
Sir, is that the RMS current rating we have calculated?
Yeah, Exactly. We are always calculating. I also told you the last session that if nothing is mentioned for a three-phase system, then you consider the RMS values and all the calculations are done in RMS. And obviously, if nothing is mentioned for a three-phase system, you go ahead with star-connected configuration only. I hope this will not be told in the exam also, and you have to assume because we are dealing with AC quantities, right? And someone tells you that I am dealing with AC mains voltage of 220 volts. If someone gives you this problem, what will you interpret from this? That obviously this is the RMS value which is being given. See, when you draw phasor diagrams, I agree that you can draw phasor diagrams of AC quantities, obviously, using both RMS and peak values. Both are true. When you can consider all in peak values or in RMS values. But general trend, what is it? It is to go ahead with the RMS values and calculating everything in terms of RMS. Hope this is clear, right? And obviously in the exams also will be given these values are all in RMS. And it is nothing will be
Sir,
mentioned
if
like
the
so you
sir,
need
in
to
the
consider
previous examples,
yes, yes.
sir, in previous example,
Previous example,
if the
okay.
suppose a three-phase star mode is there per phase, then how to calculate a current rating, voltage rating?
You do nothing. You just do it like this. See, when I am telling that you have three-phase system and you have a load connected to all the three phases, what will you do? You will just calculate the phase voltage. See, that you do. So phase voltage I will do, for example, this is 400 volts. So do 400 by root 3 because I did not tell you that it is nothing star or delta. Then inherently you need to assume that it is what star. So for star the phase voltage is 400 by root 3. It is somewhere around 230 volts. Agreed. Then that 230 volts need to
Yes.
be impressed across this particular load using the compensator. Your drop is compensated by the adding this device, right? And
Yes, sir.
this voltage will then come as rated 230 at this load point, this point. And obviously, when you know this 230 volt is this, then 230 by your load impedance is the current, and that current will flow through all this series connection, right? So then supply, then compensator, then load. So even for three phase or single phase, the problem is the same. You can just assume it as a per phase representation, like you draw single line diagrams in power systems. What do? You just draw single phase equivalent networks, right? In machines also you do like that. Power systems machine were all you do in single phase equivalent representations. But we are analyzing a three phase network. So you need to do like that. When you draw this, you assume balanced configuration. Otherwise, you have to tackle all the three phases differently, one by one, and then use the effective rule, right? So hope this is clear. Just convert from line to phase
Yes,
voltage,
yes.
and then go ahead with the same steps. Nothing will change. Compensator and remember while calculating compensator rating, just multiply by 3 into phase-to-phase quantity. Phase quantities, right? 3 times phase voltage into phase current, or root 3 times line voltage into line current. Phase to neutral, I mean to say. This is, and this is line to line, or phase to phase. Also, people say phase to phase. So both are same, line to line or phase to phase. Everything is same. So don't confuse between them. Okay. Now just see the next problem. And after solving this problem, I will give you a homework. Just post in the group. You will find some interesting results, right? So first try to solve this problem, okay? So after that, if you can solve that problem, I will understand that you have understood the whole assignment, that what type of problems can be formulated. And if you can do that, you will not face any problems while in the exam also. So just try to see this problem first and read the problem, what it is given. After that, tell me what will be your approach, right? So three things you need to calculate: current rating, voltage rating, and VA rating of the compensator for a single phase system. And consider you have now your source impedance. So source impedance is sitting just after the supply, like this. You draw it. it will be more clear. So source impedance I indicate by ZS, which is RS plus J into XS. And what is RS? RS is given as 2 ohm. What is XS? XS is given as 4 ohm. In the problem, it is already given. And after that, you have that device, that compensating device. I can just symbolize as this. After that, just assume this is VC or something, and the current is I, which is same as IS. IS is the source current, and this is VS, which is the source voltage. And obviously, you have after that the load point. Beyond that, the load is connected, which is ZL. And what is ZL? It is 15 plus J12. So this is RL, and this is what? XL. So what are the information given? That you have to calculate the current and voltage and then volt ampere rating. Now you have the source impedance here. So nowhere is it given that you have to take any kind of particular power factor at the supply side. So obviously your constant is minimum rating, right? So I told you for minimum rating you are having no control over the power factor. You lose the control over attaining a particular amount of power factor at the supply side. But you gain the advantage of having minimum voltage injection, which is in phase with this voltage. In phase with what voltage? This voltage. After the source impedance, get in phase amount of voltages to just make it equal to rated amplitude at the load point. So how will the phasor diagram look like? Can anyone tell me, or anyone can draw with me also? So this is VS angle 0, which is reference, taken as the reference. And after that, you have lost control over power factor. So I assume that it will be a lagging kind of load, because all the impedances and loads are lagging loads, as you can see from here also, because it is plus J. The impedance is plus J, means it is lagging. So the current will also be lagging. So this is IL, or you can tell this is IS, or you can tell this is IC. All are in series, right? So compensator current, load current, source current, all are same, and these are lagging in. Now this is VS angle 0, which is the supply voltage. Now after that you have the drop of the source impedance. So VS minus IL into RS minus J IS or IL into XS is the drop. After the drop, what is remaining? This voltage, which is this node voltage. I can tell it 1. So V1. So with V1, you need to inject just minimum in phase voltage to attain what? To attain same amplitude of supply. So what voltage you need to inject in order to attain minimum volt ampere rating? It is the voltage. This minimum voltage straight in phase with V1. So now I can attain VL, which is equal in amplitude, whose magnitude is equal in amplitude to the amplitude of the supply. I can tell. So now this angle I can tell VS and IL or IS. These are all the supply power factor, which is beta. Beta is nothing but supply angle or supply power factor angle, I can tell, because it is the phase difference between the supply voltage and the current. And obviously, can anyone tell what is the load side power factor, which is the angle between PL and IL? PL and IL means this power factor. This I can tell as theta. Agreed or not? Right? So now can anyone tell me what is the current rating? Current rating is the easiest thing I told you. So what can the current rating be calculated? How? So IL is VL by ZL. This always holds. Obviously, remember this is the mod. So mod VL by mod ZL, you get the amplitude of IL, and same IL equal to IS equal to IC. All are in series. Current calculation is the easiest. So just calculate what is the value. 220 by ZL. ZL is what? Root over 15 square plus 12 square. What is it coming? Just calculate. Getting 11.45. amperes, right? First problem is done. Now what you want this amount, this voltage injection, because you want to find the voltage rating of the compensator. You want to find the voltage rating of the compensator, you need to know the amplitude of this voltage, that what amount of minimum voltage I must inject so that my voltage amplitude at this load point is same as that of the amplitude of the supply or the rated voltage. So in order to know that, you need to know the amplitude of this injected voltage, which is from here to here. Here. So how to find this voltage amplitude? What is the method that you will follow to calculate this voltage amplitude? Either you can do by geometry, by phasor diagram, or what is another method that you can follow? You can do by network analysis also. No, not denied. But another point is that you can do it by power balance. So power balance means, since you have the source impedance also, you need to inject this voltage. So you need to do both active and reactive power balance, because it is not unity that it is only active power. You have both active and reactive components of your voltages, right? As you can see, this injected voltage is not in line with the supply. So it has both active and reactive power. Agreed or not? So both active and reactive power balance you need to do, because you have two unknowns, right? You have this beta and you have this theta is known, right? Load power factor is known. Load power factor is known from the ZL. But this beta, which is the source end power factor, you have to calculate. It is still unknown. And this voltage amplitude is still unknown. So these two are the unknowns, right? So if you write the active power balance equation, what it is? You have Vs mod Vs into mod, I can tell, Is or IL. All are after compensation, okay? Into cos of beta. This is the active power. Plus, this is the supply. From supply, you got this amount of active power. Plus, V compensator into IL, because current is same, into some cos of theta. Because cos of theta will be this voltage, the compensator voltage, this much, and it is having angle theta with IL. So obviously, the active power is cos of theta. Vc into IL, Vc is this amount of voltage which is injected, that we need to determine actually to calculate the voltage rating of the compensator. So I denote it as Vc. And as per the phasor diagram, you see the angle difference between Vc and IL. IL means the supply current also, because it is in series connection. So all IL, IC and IS are in series. So anyone you can assume. So the angle difference is theta, which is the load power factor attained by this ZL. And this is the active power. So these two active power will be dissipated where? It is Is square RMS square into Rs plus Is RMS square into RL. Agreed or not? Is the statcom or compensator, I can tell. This is supplied actually, and this is dissipated, consumed, I can tell. So supplied equal to consumed. I'm doing just that, power balance. And also Vs into IL into sine of beta plus Vc into IL into sine of theta equal to Is square into Xs plus Is square into XL is the reactive balance. And everything you know Is is what? 11.45. So Is or IL or IC, all are Is equal to IC equal to IL, all are known. Is 11.45. Bc we need to determine. Theta, what is theta? Theta is nothing but load power factor. It is tan inverse of 12 by 15. So what is theta? Can anyone calculate what is theta coming? Tan inverse of 12 by 15, right? So around 38 degrees it is coming, right? So this angle also is known, theta. This is 38 degrees. Just put it in here. And what else you need? IS, you know. IS is, I told you, 11.45. What is XS? XS is given. Source impedance is 4 ohms. What is XL? Load impedance, load reactance, I can tell. It is 12 ohms. And what is RL? RL is known. RL is what? 15 ohms. What is RS? RS is given as 2 ohms. IS is already known. Cos theta, theta is 38 degrees. Beta is unknown. So two unknowns, two equations. Beta you don't need. If you want to calculate, you can calculate. But what is the main point we need to calculate is VC. What amount of voltage is injected by the compensator. So you do just what? You know sine square beta plus cos square beta is 1. So you square and add these two equations. Because this side is known, right? You just calculate IS square RS plus IS square RL. Is a number that will come. So just calculate. Let us calculate and then see what it is coming. Okay. I will just calculate for you. First time I will calculate. Okay. So I just write this equation here and write all the values. And you also do with me, because this kind of problem you will have to tackle more frequently, because most of the problem will be like this only, not VS into IS into cos of beta plus V compensator, which we need to calculate, into IS or IL, anything you write, all are same in series connection. Okay. So cos of theta equal to IS RMS. Obviously this is RMS. IS RMS square into RS plus IS RMS square into RL. So this is source impedance resistance and this load resistance. And another equation, how will you get? Sin beta plus VC into IS into sin theta equal to IS square into XS plus IS square into XL. Now I know RS, XS, RL, XL, and IS and theta. All these are known. So IS is 11.45, theta is 38 degrees. All you know. This is 2 ohms, this is 4 ohms. What is RL? RL is 15 ohms. This is 12 ohms. Now what I'm trying to tell, this side you know completely. So if you just plug the values, can you tell me what are the right hand side of these equations?
Two zero nine seven.
Just let me calculate. Yes.
2097.
Yes, this is 2228. I'm getting. And this one I'm getting as sorry, this is Excel, okay. Two 098, I can tell. Theta, you know. What is theta? 38 degrees. So just calculate what is IS cos theta and IS sin theta. Well, IS cos theta, just calculate 11.45 cos 38. It is around 9 amperes, right? Sin 38 you also calculate. Around 7 amperes. So to simplify, and VS and IS you know. VS is what? Oh, VS also you write 220, right? What is the voltage? 220 volts. Yes, it is 220 volts. So just calculate what is VS into IS. 20 into 11.45. So 2519. So I can simplify. 519 into cos beta plus, I can write IS cos theta as 9, right? 9 VC. VC is unknown, okay? We need to determine. Equal to 2228. And another equation is 519 sine beta plus what? VC into IS sine theta. So 7 VC is equal to 2098. Agreed or not? Now eliminate beta. What do? You just write it as this 2519, or I can write like this 2519 cos beta is 2228 minus 9 VC. And also you write here 2519 sine beta is 2098 minus 7 VC. And you square and add. Simple. What it is coming? 2519 square. Sine square beta plus cos square beta is 1. So squared and add. So 2228 minus 9 VC whole square plus 2098 minus 7 VC whole square. Break it and go ahead with me. What it is coming, let us solve it. 8 whole square is 4963984 plus 81 VC square plus what is this 2098 square, okay, which is 4401604 plus 49 VC square, and now you have minus 2 times this into this. So times 9 into 8 plus 2 times 7 into 2098. So minus 69476 into VC. So simplifying, you can take it as this side and form a quadratic equation. So the quadratic equation will be, I am writing in red colors. So we need to add these two and subtract from this, right? So what it is coming, 4963984 plus 4401604 minus 2519 square. Okay, it is coming as, so the constant term is coming as this, and then you have some VC terms, which are these three are covered. So this is minus 69476 VC, and the square term is coming from these two as 81 plus 49, which is 130 VC square equal to 0. So can anyone determine the values of VC? You can just use Sridhar Acharya's method, or factorization will be too difficult. So use Sridhar Acharya's method, where it is for ax square plus bx plus c equal to 0. You have the roots as x equal to minus b plus minus root over b square minus 4ac by 2a. Just apply. What are the values of VC that are coming? I will also solve and finish, or when you have done, just let me know. Just apply this. Okay. Just compare the coefficient. This this, p as this, p as minus 69476, and this is c. Anyone, if you are done, just let me know. Okay. I am also solving. So I have calculated, but I will give you some time and just calculate and let me know. Okay. It is easy, right? Just plug in the values and just determine. Just take your time, and when finished, just let me know. So 130 into VC square minus 69476 VC plus 3020227. I want to find VC. Two roots will come of this quadratic, and just I will write the roots. It is 47.73 and another root is coming as 486.69. So two roots of this quadratic are coming. Which one do you think I will take? First one or second one? Anyone? Yes, am I audible?
Yes, smallest value.
Yes, why is best? Any
You have to
arguments
minimum,
you
no?
can? Correct. Minimum value. So you can write as minimum, right? So 47.73 is the voltage rating that you have to inject. Okay. So what it was asked in the problem, voltage rating. So it was 47, around 47.73, because we have done some approximation. So around 47.73 is the answer. So now you know V of C mean mod, obviously the magnitude is 47.73, and I of compensator we determined. What was it? Can you tell me what was the current? 11.45, right? I hope the ink is visible, right? Or I will change the color. So IC is this and VC is this. It's 47.73 amps is VC mean. Okay. The minimum voltage rating. If you inject this much voltage, your amplitude will be load point at the amplitude. That voltage will be same as amplitude of the supply. So these two are the thing. So this is the first part answer and this is the second part answer. And what is C? C is asking you to calculate kVA of the compensator. Minimum kVA rating. Now current is obviously the same. It is fixed. The voltage rating minimum we determined using power balance, or you can apply network theory and solve it. It will be complicated because you have to tackle multiple node voltages. Both can be done. Both are allowed, and you can determine actually what is the voltage, minimum voltage that the compensator will have to inject. And the minimum kVA rating of the compensator is mod of VC into mod of IC, which is coming as what? 47.73 into 11.45 is 546.5 volt ampere. Okay. But if someone asks you what is the minimum kVA rating, you need to convert volt ampere to kVA and give the answer in kVA. So 0.5465 kVA. Clear? So if answer is asked in kVA, give the answer in kVA. If answer is asked in volt ampere, give the answer in volt ampere, right? So since answer is asked in volt ampere, in this problem, to give this answer as 546.5. But if answer was asked in kVA, you give in kVA by dividing by 1000. So whatever is asked, you give the answer in that. Everything is MCQ type. Okay, so units are important. So now let's go to the next problem, right? So just read the problem. And if anyone has any doubt, they can ask in between, right? Just read the problem and then let me know when you are done.
Sir, I have a small query in the previous problem.
Yes.
Sir, for the calculation of load current, why you are not considering the source impedance in series with the load impedance, sir?
Because if in the problem it is mentioned that you have
Sir.
a compensator which is used. Okay. series compensator. And what is its job? Its job is to maintain appropriate rated voltage at the load terminals. Once you are given this information, you are asked to calculate the current. What is they asking? They are asking that you need to calculate the current after compensation. When I mean after compensation, it means that using proper control technique, you have already injected appropriate amount of voltage using compensator to bring the voltage or to pull the voltage up to the rated amplitude. Once you have pulled the voltage up to the rated amplitude, your load current is bound to be VL by ZL. VL is known, which is 230 or 220 volts, divided by ZL is the IL. It is series. So obviously there is an assumption, there is a hidden assumption in this problem, because they can also ask you prior to compensation. So prior to compensation, I will not do like this. You must have attended the previous week session also. So there I solved the last problem. There I just what I did, I considered the normal network theory and Z total, the source impedance plus load impedance, total impedance, voltage divided by total impedance is the current. But why we are doing like this here? Because it is what it is asked after compensation. Okay. Because you have introduced the compensator. So whenever they ask you like this, you need and nothing is mentioned, you need to assume they are talking about after compensation. But if they ask
in before compensation, we need to add both the impedance. After compensation, we need to consider only load impedance. Yes, sir. Thank you.
Why only loading? Because you know that load point voltage. This voltage is known.
Yes, sir.
But if someone asks you to calculate the current along with the angle, then you have to take into account the angle of this voltage and angle of this, whatever is the angle of this voltage, I can tell, and angle of this impedance. How will you determine the angle of this voltage? By using the appropriate phasor diagrams, and also you can use. How will you calculate? If I ask you, how will you calculate the angle of this voltage? What will be your answer?
VL at an angle 0 degrees. 220 at an angle 0.
No, it will not be 0. No, it will not be 0 degrees. You have seen also in this problem, right? Is it 0 degrees? What am I asking you? This is the delta. This is the delta.
Okay, delta.
So if I ask you this delta in this problem, by assuming that you have attained minimum, then what you need to do, you need to do all this and determine beta first. And what is delta? Delta is beta minus theta. Theta is known from load information. Then it would have been the whole steps you need to follow and determine delta. Delta is beta minus theta. Either you do in this way using power balance, or you do using normal network theory topology. But in that case, you need to know this voltage.
Okay, sir. Thank you.
For this voltage, you have to apply geometry, which is complex because you need to do the angle calculations. So that's why I prefer the power balance technique, because there you don't have to use geometry. Why geometry? Because the voltage amplitude you need to see is equal in both the cases, and geometry will help you determine the angle. It is possible to determine the angle using geometry. Once you know that angle using geometry, you can go ahead and calculate with network theory. So only this VC is preventing you to calculate this delta. If I give you this VC, what you will do? VS, V source plus VC, some VC if I give you, will give you this point voltage, node voltage by normal network theory. But what is preventing you? You don't know actually what is VC. You need to do by phasor analysis and geometry you need to determine in order to pull this voltage up to the rated voltage. You need to draw that phasor diagram, that circle, and determine the angle. So that is why we do power balance. And we deploy this VS as VL and IL and IS are all same. And using the given known relationships and the network topology, we try to determine first the angle beta or the voltage VC. Once we know the voltage, then it is easy. Because we know the angles, right? Okay. So now you can
Sir, your voice is breaking, sir.
Yes. Hello.
Sir, you are not audible.
Yes. Am I audible? Hello.
Yes, 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 sir.
Sorry, there was some network latency. So let me start presenting. So the screen is visible, right?
Presentation is yes. Nothing is appearing on the screen. Black screen.
Just give me some time. I will represent it.
Yes, yes. Now it is visible.
So just read the problem. So it is a three-phase
Sir, I
supply
have doubt
system
in previous
and
problem, sir.
400 volts.
Sir, if
Yes.
in the previous problem, if suppose it is a star connected system, sir, load, then procedure will be same.
In the previous problem, 1 second. Let me. So screen is visible. I think some latency is there. Is the previous problem visible?
No, sir.
So let me again stop and again start presenting.
Hello.
Yes, sir.
Yes, sir. Audible.
Okay. So timing, because I think there is some slow. So hope you are able to see the screen.
No, there is black screen, sir.
See, and let me. Hello. Is hope now I am audible? Yes. Hello.
Yes, sir. Audible, audible.
Yes. Just let me know whether the screen is visible. Okay.
Have you shared the screen, sir? Shared screen is not visible. Yes, it is visible now.
It is visible now.
Okay. Okay.
It is visible now.
So slides are moving, right?
Yes, yes.
Yes. So the problem is, am I audible and my screen and me are also visible, right?
Yes, yes.
Okay. So now we can resume. Sorry for the latency. It has some network issue. So a three-phase AC supply has a 400 volt and feeder is having that is the line feeder. The resistances are given. You can consider it to be the source impedance as 2 ohm and 4 ohm inductive reactance. And now your question comes, which is the balanced star connected load. So now it is a three-phase supply system, and it is not mentioned it is star or delta, but you have to assume star. But the load is given to be of nature star. So 20 plus J15 ohm per phase is connected. So it is like the previous problem, only a three-phase version of that. And a self-supported DC bus is there, which is used to raise the voltage, same as that of the input voltage. But the problem is very easy. It is just asking you to calculate the RMS current. Now your point will come how we do it for three-phase systems. Just tell me who was having some doubt regarding the three-phase. Can just tell me. In one line, you can just tell me the answer. So how will you do it? You know per phase load impedance, which is 20 plus J15. And what is the phase voltage? It is 400 by root 3. Can you draw the diagram how it looks? So it is nothing but like this. You have some voltages. This may be A, B, C, and you have the load, three-phase load, and this is A point of load, B point of load, C point of load, and you connect them. So hope it is clear. Who was having problem? Hello. So what will be the single phase equivalent network? Now I put in some compensator. So you have some here ZS, some ZS is here. And after ZS, I connected that device. Here all. After ZS, okay. I connected the device. And here also. So picture is clear, right? The single phase equivalent, how will you do? Draw a single phase line and then you draw the ZS and then you draw this V per phase, okay. And then you have the device. And then you have the load. ZL. What is current? Load current, VL by, now VL, you know, all the load points are having rated voltage, mod, okay, by ZL. So this IL equal to IC equal to IS. What it is? 400 by root 3 by 20 square plus 15 square. Answer, you just calculate in one line. Just let me know the answer, what you are getting. Then 9.23, right? 9.23 amps or 9.24, I can say. Everyone getting it? Or you have some doubt? You can tell me. So all is same, just it is three-phase version of the problem. And current calculation is the easiest. You can do in one line. Only voltage calculation, you need to see whether it is UPF or whether it is minimum kVA rating. Those two variants are there. Anything you other than particular power factor you need to do, then you need to do by power balance. Otherwise by geometry, which is you have to find the angle and then you need to find that beta or that VC, and then accordingly you calculate whatever is asked. So that is the thing. So this problem is clear or not? Please let me know. Hello. Any doubts? I hope I'm audible.
Yes, sir.
Hello. So this
Yes,
is
sir.
clear or not? Huh.
Yes, it's clear.
Yes. This is the three-phase version, okay, which you were asking.
Sir, in previous problem, we have seen that for the single phase, no? But if it were a three-phase system, then we have to go like that, no? And rest of the things will be same in previous problem.
Yes. Previous problem was for single phase. If it was three-phase, you need to have done the per phase and then you need to have proceeded.
Okay, thank you.
Other than that, everything is same, and current calculation is very direct because everything is in series. You know that load point voltage after compensation is same as rated voltage. You know the magnitude, you know the impedance magnitude, and then you divide them and determine the current. And every same current will be flowing from the supply, then through the compensator, and then to the load. This is just direct, okay? But please note whether the three phase or single phase. Very important, okay? By √3 factor will come. And also in KVA rating, if they ask you in the second problem, the KVA rating, for example, then also you need to be cautious that you need to have a 3 times that factor of part phase. Okay. Please note that. Okay. Is it clear?
Yes, sir.
Yes. So it is very important and you can do many mistakes there. That is why it is very important to see what is the system. Maybe you can draw a small diagram. If you want in exam, before exam, if you practice, you will not be requiring to draw diagrams because you will be practicing and then you will be doing the assignments also. So that will be easy. During the exams, it will be becoming easy for you. So now let us move on to the UPQC problems. So UPQC, I already told you that it is a combination of the series and the shunt compensators. Both are connected in the same DC link. And then it provides both the voltage quality and current quality features. So now you have, and also you must know that UPQC-Q, UPQC-P, and UPQC-S, what are they? The UPQC-Q can only inject quadrature voltages, UPQC-P can only inject inline voltages, and S can inject any type of voltage you want. So these are basics, and using the phasor diagram, you can just see. So just we draw many phasor diagrams. I hope you must be clear with the series compensator phasor diagrams that are very helpful while solving the UPQC-Q problems, or because you have got a feel of that also, that how the voltage compensation works for the series compensator problems. So the UPQC problems will not be that difficult, but obviously the UPQC problems will give you more insights that how the compensators are actually working together. So let's solve a few problems. You will understand what I am talking about. So first read the problem and then let me know. Note that it is a UPQC-Q, okay? So the voltage injected is in quadrature with the supply, right? So this type of UPQCs inject reactive power, right? As you must have seen in the lecture also, because they inject reactive voltages or quadrature voltages. And the problem is very simple because it is asking you to calculate the DVR, that is the voltage restorer and RMS current, and in amperes during the sag condition. So but just draw the how they look. Just if you draw, you will be getting some insights. So single phase equivalent, if I draw, some kind of supply is there, and then you have the this in this problem there is no source impedance. Let us neglect it for the time being. And you have that device, and you have the IGBTs, and you have connected this like this. So all the inductors and all those things are there, the body diodes. So you just, and you have the DC link sitting in between them, and you have another pair of IGBTs. They are sharing the same DC link, okay. And from here, if you draw the single phase equivalent, this is going to ground, and this is coming with the interfacing inductance to the line. from here. And after this, you have the load. Maybe I can shift it a little bit. So after this, so this is the line. I can draw it with different color. So this point is the line and they are attached in series and shunt. Okay. This is connected in series and then after that you have the line. And this line, the statcom is coming here, right? In shunt. And this is coming in series. So this is series, this is shunt. And then you have the load. Now, supply side is facing a sag, 20% sag. So can you tell me what is the RMS current of the DVR? It is easy, very easy. Now calculate the active power of the load. Now problem you understood, right? What it is asking from you, right? So same like the previous problem that you need to calculate what is the power. What is the power? The power is √3 times I can tell VL into IL. IL is what? 60. The load details are given here into power factor. So what is the value coming? Just tell me. Power you first need to calculate, okay? To 60 into 0.85. It is around 36,658 kilowatts. And after sag, I think at the supply side, because it is asking you to calculate DVR RMS current, means this supply current. Supply current and DVR RMS currents are same because they are connected in series. So after sag, what is the voltage? After sag voltage, supply voltage I can write. What is supply voltage? 415 into 1 minus 0.2 or 80% I can tell. Voltage becomes 80% because 20% sag is there. So voltage becomes 80% of previous. So this is line voltage. Okay. What is line voltage? I can also do 3 times phase into phase to phase voltage into current, phase current. Phase current and line current for star are same. So anyways, √3 into line voltage into line current into power factor you do, or it is equal to 3 times phase voltage into phase current and line current are same into power factor. Both will give you same results. So 80% of voltage, what it is coming? 80% of line voltage, 0.8 times 415. So it is coming as 332 volts. So now the supply voltage is 332. With that, you have to meet the same power demand. So what is the current? It is nothing but, what is the current? New current, IS prime, I can tell. It is nothing but 36658, this power divided by voltage. So what is it coming? (36658) divided by 332. It will be √3 into VL, right? This is 3-phase system, right? So current is power by √3 times VL, right? Okay. So it is coming 36658 divided by √3 times line to line voltage. So it is around 63.7 amperes. 63.7 amperes. So everyone understood why I am doing like this? It is like the... Hello, am I audible? Hello.
Yes, sir.
Yes. So after sag, that is after the voltage sag, your voltage became 80%. That you understood, your line voltage. So power divided by √3 times the line voltage will give you the current. This point is understood or not? Because the UPQC queue is only injecting the reactive power. So current, while calculating the current, you take the active power divided by √3 times the that is processed in the line. Okay. The active power that is flowing into the line, you take that active power divided by √3 times the line to line voltage after sag will give you the current. That is the line current or the DVR current, anything you can tell. So this is the concept. Okay. So next, let's move on to the next problem.
So hello, sir.
Yes.
Hello. So why are we
Yes.
dividing by root 3 there? That active power by root 3
This is a 3
into 99.
this is the 3. This is, see, what is active power? It is root 3 times VL into IL.
Yeah. Okay.
Okay, into cos phi.
Mm-hmm.
So what is IL? It is P by root into VL into cos theta.
Okay.
Now, since the UPQC Q is only, that is what I am telling, I have already included that in the power, right? So this is 36658, right? Which I determined from the load power factor. This power needs to be, because the UPQC Q is doing what? It is only injecting reactive power. No active power it is injecting. So whatever is the demand of the load, active power demand of the load, needs from the supply side. So I hope that is clear. And you need,
Yes,
you know
sir.
that you
Yes,
have to provide reactive power. You just see what it is written. To provide reactive power compensation at unity power factor at the AC mains. So unity power factor means cos theta at the supply side is 1. So what do you do? Just the power balance. P divided by root 3 into VL is the current. Because cos theta is 1, right, at the supply side. You just read the problem.
Understood, sir.
Okay. So now after doing that, you calculate that the supply current is 63.7 amps. Okay. So these are very basic problems actually. The UPQC is much easier actually, I can tell. So just see the next problem. This is also one line problem. Everything can be done in one line. So just read it, and after you finish reading, you just let me know. So after that, I will give you a homework. Actually, you will find an interesting result, and you can tell me in the group that what it is coming, because that will give you more insights. So after this problem, maybe I can give the homework such that you can solve it and check. Just see this, it is a one line problem. Okay. After you finish, you just let me know. Yes, done. Yes, hello. So I think all types of problem we have covered on already. So maybe 2 to 3 variants of UPQCs we can cover more, and then UPQC topic will be over, I think. There are 2 to 3 more variants, but before that I want to give you one homework such that you can solve and check. After that only we can tackle those 3 variants, and maybe after that we can move on to the filters. But before that you need to do that homework and just see. Other than that, after 3 to 4 problems, this topic can be done, completed. So before that, you just solve these 2 problems, and after that I give you the homework. So first, so I think I can take 10 more minutes. Hello. Anyone, if having some problem, this session is recorded only, so but I prefer you stay and just be interactive in the session, because those sessions recordings will not be helpful for you, because until and unless you understand and ask your doubts, because it is the session which provides you the platform to ask the doubt. So maybe you can interact and get your doubts clarified. Maybe some new concepts may also evolve by discussion. So it is always encouraged that you participate in the discussion and ask as many doubts as possible, right? So if you have some doubts, you can ask. So just try and read this problem and maybe we can solve it in one line. So it is very easy actually. So everyone comfortable with the term UPQC P, right? This is a UPQC P that is written. So what is UPQC P meaning here? Anyone?
It is in line with the
Yes,
supply
yes.
voltage.
Yes. What?
In line with the supply voltage.
In phase with the supply voltage, yes. That kind of voltage it can actually inject. So now can you calculate the RMS current? Same. Other than that, it is same. The functionalities that it is providing is the reactive power compensation of the load to maintain unity power factor and also the voltage regulation. So both current, that is as per the reactive power the shunt is providing, that is the DStatCom, which we have already discussed as the DStatCom feature. And what is the DVR doing there? It is just injecting appropriate amount of voltages in the line such that you can get at the load point the rated voltage. These two features are there. Simple. And how is it injecting voltage? In line with the voltage, supply voltage, I can tell, because it is neglecting the line impedance, okay, or source impedance, you can tell. So knowing these two information, you need to calculate the RMS value of the line current, the or the compensated, okay, the compensated value, okay, during voltage sag condition. So same, using power you can calculate, right? The load information is given, right? So what is power? It is 220 into, this is single phase, right? So 220, this is VRMS into IRMS, I can tell, into 0.9, right? What it is coming, just calculate. So I can take 10 more minutes, right? Just finishing these two problems and we'll give you the homework, right? So it is coming 4356 watts. So solving this, you get what is the current anyone? You know the voltage. The voltage at the load point is same as the rated. So what is IL? It is nothing but 230 or 220. What it is given? 220 divided by, or powered by, I can say. This is a single phase. So powered by voltage. So what it is coming? But you need to calculate during the voltage sag condition. Please note. It is important. So power remains the same. Only voltage. What will be the voltage during sag condition? It will be how much sag? 15% to 75% of the voltage. It will be during sag condition. So power is same divided by voltage. V sag I can tell. V during sag is 75%, 0.75 of the rated. So what you are getting? Tell me. IL during sag. What it is coming? (26.4 amperes), right? Oh, sorry, 0.85, not 75, 85%, right? 15% drop, so 85% still remains. So 23.29, it is wrong. 23.39, okay. Just calculate with me so that it is helpful. 23.29 amps. So this will be the thing. So now let's move on to the next part. So what is during the RMS? This is same, right? Okay, the DVR and the supply current all are in series. So this compensator I can tell is same as IL sag, or everything is in series. So 23.29 amps. Just target the next. What is it? The voltage rating of the DVR. So since the DVR injects in-phase voltage, so 15% drop. So 15% drop voltage it should inject such that its amplitude is same as the rated. So 15% of 220. This amount of voltage is the V compensator. So what is it? 0.15 into 220. 33 volts. It should inject in line with that of the supply. That's the sagged supply, I can tell. So it is like that. So it is 33 volts, right? And you know that the voltage injected is 33 volts and the current is 23.39. The kVA rating is, or the VA rating, I can tell, volt ampere rating is what? 23.29 into 33. The current into the voltage, IC into VC. I compensator into V compensator, right? What is it coming? 23.29 into 33. So it is 768.7 volt amperes. It is easy, right? So the 4 parts are done in one line. So just see the next problem. Shall I take it up in the next class, or you want me to solve in this class only? Because there are still 4 to 5 problems that are remaining in UPQC before we move on to the next topic, and maybe we can finish it within the first half of the next session. So you want me to take it in the next class, or you want me to do it now? Because I also want you to give the homework. So the homework is, first let me give the homework. So for this problem, just take a screenshot of this problem. You just see whether the volt ampere rating is changing by changing the load to leading load. That is, you consider 15 minus J12. 15 for 15 plus J12, I already calculated this problem. So you just take the same problem and do 15 minus J12 and see what is its impact. That is, by changing the nature of the load, I want you to analyze what is the impact on the compensator rating. You just calculate it and let me know, okay? You will get some insights that how the load also can impact the selection of the minimum kVA rating of the compensator. Just I wanted to it was interesting, and you get some insights that how can the load also help the compensator to attain the features, functionalities like that. So this is homework. You just take the load as 15 minus J12 and just send me the screenshots of your solution. So both for with the lagging load, ZL equal to 15 plus J12, which we already did. You do it in first half, and in second half you take it for 15 minus J12. So just see whether it will be changing or not. Anything will change or not. Okay. So that was the homework, and remaining problem we can take in the next class. Okay. 4 or 5 problems are there, and we can just end the topic of these compensators. Okay. So, okay, we can end the session. If you guys have any doubt or want to ask anything, you can just ask. Okay. Or else I will end the session. Any doubts? Okay, so I will end the session. Okay, you can leave. Okay, thank you.